Hello everyone, my name is Jianping. I'm from Chinese Academy of Sciences, Institute of Information Engineering. It's a great honor to participate in the SISTER 2022, and I will introduce our work entitled TACC Secure Accelerator Enclave for AI Workloads. Motivation and background. AI workloads today is typically performed by heterogeneous systems, which includes CPU acts as a host control unit and a set of device accelerators for parallel acceleration, and the accelerator architecture for neural networks will play an increasingly important role. However, existing TEs do not support many heterogeneous units and connections, like GPU, TPU, FPGA, and more other accelerators. TE only based on CPU architecture can no longer meet the security requirements of the whole heterogeneous system. The industry urgently needs to cover the entire heterogeneous system architecture with the protection scope of the secure enclave. GPU memory hierarchy is managed by its device driver resident in untrusted host OS, and almost all modern discrete GPUs implement a unified memory, and all memory of the CPU and the GPU are paged and recycled by the OS, and interact through the PCIe bus. GPU driver uses the MMIO path to update GPU context, such as the channel descriptors, page directories, and page tables. After the context is updated, the XDMA engine on the GPU performs memory page copy, and the IOMMU on the CPU is responsible for the adjust checking. If page faults are encountered during kernel execution and the missing page are not in the GPU local memory, then file page faults will interrupt to the host OS to request paging service. When the host OS is untrustworthy, the GPU's memory and state control registers will be leaked and tampered with, and the communications between the host CPU and the device GPU also has the risk of side channel leakage. We refer to popular AI accelerator designs such as Cambrian series and TPU, and summarize a brief accelerator memory hierarchy in Figure 2. Accelerators usually do not have a complex multi-level cache (TLBs). Instead, they use on-chip buffers. Some local MMU designs for accelerators have recently appeared, providing a unified memory space similar to GPUs, supporting adjust space virtualization and on-demand paging. But they, like GPUs, still rely on host OS support, while in this paper, it is assumed that the host OS is not trustworthy. So the internal memory of the accelerator enclave needs to be isolated from the untrusted OS and other software. Early TE researchers mainly focus on CPUs such as AES-GCM. In recent years, there have also been studies to build GPU TE by extending CPU TE, such as Graviton and HIX. Telekinesis is based on GPU TE, similar to Graviton, and moves the user app and the GPU runtime from the cloud platform to the client to improve security. HIT uses physically sealed chassis to construct a rack-scale heterogeneous T, which supports all existing computing resources, but its reporting-based context clearing mechanism reduces the utilization of the distributed heterogeneous resources. However, none of the previous studies involved the trusted reconstruction of the emerging accelerator architecture itself. Our TACC is the first such design that supports hardware accelerator enclave, with unique isolated management mechanisms between in-package running memory and external memory. With the advancement of 3D IC packaging technology, the integration of a considerable scale of in-package memory on one chip in the foreseeable future will become the mainstream. The memory outside the package is easy to snoop and tamper with, while it is difficult for an attack to snoop in-package silicon interconnection between the accelerator die and the stacked memory. TACC uses the physical isolation of in-package and off-package memory to effectively isolate the internal memory from the untrusted host OS. TACC architecture. This is the overview of the TACC design. We adopted the popular accelerator core and add several critical models for building Secure Enclave to the memory access hierarchy of the accelerator. DSC, the device security controller, address checker, and the AES-GCM engine with a DMS. The gray shaded area is the untrusted space, mainly controlled by the untrusted host OS, and the transparent box is the secure world. We can see that 3 trusted nodes, remote user, CPU enclave, and TACC enclave share the same set of AES keys. To implement a 3-party encrypted communication channels, TACC cuts off the MMIO path for the host CPU to direct access the accelerator. All data and code are in the form of encrypted packets and are transmitted by the XDMA on TACC through PCIe interface. A pure XDMA driver decoupled from the TACC runtime is installed in our host OS to serve the beliefs relay. Therefore, untrusted OS and other software can only access TACC off-chip mem0, the ciphertext communication memory, while the on-chip mem1 plaintext running memory is only visible to the CPU enclave bound to the current TACC enclave. We consider a strong adversary, who is the host OS and other third-party software running on the CPU. The attacker will try to use the shared IO-MMU mapped space and shared PCIe root complex of the host CPU to snoop or even tamper with the memory and the register space of an accelerator. Since the space exposed by our TACC to the host is only the ciphertext memory outside the chip package, while the plaintext running memory inside the package is not visible to the host. Therefore, TACC can prevent these attacks and ensure that the data and the calculation process inside the TACC enclave cannot be observed or tampered with. TACC puts the AI workloads inside the enclave to can prevent black box probing by third-party attacks. But if the network code provided by the enclave user itself has errors, or the user input samples are already noisy, TACC cannot defend against these adversarial attacks. However, the value of isolated execution environment constructed by TACC is to prevent third-party software attacks from spying or tampering with the AI network and samples inside the enclave. And only the enclave user itself can operate the internal sensitive content. Therefore, evasion attacks, poisoning attacks, and more general adversarial attacks are orthogonal to our TACC design. Assume that the adversary cannot break the CPU enclave, hosting the TACC runtime and user app, such as the side channels and control channels of SGX are outside our scope. Assume that the chip package is creatable. The internal memory cannot be snooped by an adversary who physically touches the chip. In addition, denial of service attacks are outside the scope of this paper, and physical leakage methods such as electromagnetic and temperature for the chip circuit are not within our scope. 4 types of secure channels supported by our TACC. The remote command channel is used by the remote user to send TACC enclave creation and destruction requests. The local command channel is used to allocate and reclaim the internal running memory of TACC in the user app program in the CPU enclave. The task code channel is used to transmit the code instruction string executed by the accelerator core. The task data channel is used to transmit the data to be processed by the accelerator core. Note that after the AI code is deployed, the encrypted data can be directly transferred from the remote user to the TACC accelerator. That is, step 2 in figure 3 can be skipped. DSC and adjust checker. TACC maintains per accelerator core memory occupancy table of the current task in the address checker to implement the memory access permission check. The DSC is responsible for set or clear the table entries through dedicated TACC malloc, TACC-free instructions. TACC uses direct addressing and divides the on-chip memory into large chunks. For example, if the on-chip memory has 4 GB space, we can equally divide it into 128 chunks, each with 32 MB. In this case, TACC only needs to implement 128 entries in the task memory occupancy table, as shown in Figure 4. TACC currently only supports static allocation of memory chunks. That is, all memory chunks required by a task must be allocated in advance before the core calculation can begin. All memory access requests sent from the accelerator core must go through the address checker to check permissions. When the remote user finishes using and destroys the enclave, all buffers in the corresponding accelerator core are cleared, and all table items and physical memory chunks occupied by it will also be cleared up. TACC instructions. Security primitive instructions TACC enclave create or TACC enclave destroy and TACC malloc TACC-free are both executed by DSC. DSC ensures that when the accelerator dynamically switches users to create or destroy enclaves, all on-chip buffers and occupied in-package memory are physically cleared up. DSC actually include functions such as secure boot, remote attestation, and three-party key negotiation. Only a DSC can access the device root of trust, the endorsement key, and randomly derive the RSA attestation key and AES symmetric key for different user enclaves. And every time the device is powered on again, the DSC secure boot flow clears all on-chip buffers and in-package memory by default. Except for security-related instructions, all other instructions are task instructions executed by accelerator core. We divide TACC task instructions in two types, memory access and calculation, since we implement multiple buffers that can be accessed simultaneously in accelerator core, but not all instructions need to access all buffers. Therefore, we add a field indicating the buffer's mask for selective access to multiple buffers. And since the physical address of on-chip buffers is directly open to programmers and compilers, mask allows users to flexibly choose to concurrently access some buffers. Figure 5 shows the memory access instructions formats supported by TACC, including tensor load, tensor store, tensor copy, and tensor clear. Figure 6 shows the calculation instructions formats supported by TACC. Currently, only convolutional layer, fully connected classifier layer, and global average pooling are supported. For convolution and fully connected layers, different opcodes can distinguish whether to accumulate and whether to activate. For pooling calculations, additional execution units are required, and the calculations instructions are collectively referred to as tensor execute. Program model. Figure 7 shows the TACC application snapped inside enclave. All memory chunks to be accessed by the current task must be explicitly allocated by the programmer, and then the task kernel code can access them. And finally, the memory chunks need to be manually freed by the programmer. If all memory chunks are used by a task kernel, and space exceeds the capacity of TACC in-package memory, programmers also need to manually swap memory chunks to off-chip memory. Memory chunks must be encrypted, decrypted when swapping out and swapping in, with integrity check. Figure 8 shows a TACC sample enclave interface definition. TACC requires at least two types of equal functions to transfer remote commands packages and task C code package into the CPU enclave. Similarly, two types of O-code functions are needed to transfer local command and TACC binary code packages from the CPU enclave. Figure 9 shows the uplift relay preset code using the XDMA driver in the untrusted OS to read and write off-chip memory of the device. Uplift relay can forward the ciphertext local command and TACC code binary packages from the CPU enclave to the TACC device. And for large batches of TACC data from the remote user, they do not need to go through the CPU enclave and are directly relayed to the TACC device, thereby reducing the number of encryption and decryption. Prototype evaluation. We chose RepVGG, a zero inference network, as the AI workload to evaluate our prototype TACC on the FPGA, and we have implemented two versions of prototype: a Xilinx core with 36 multipliers and a fat core with 144 multipliers. The FPGA logic resource occupancy of the two versions of the prototype are summarized in Table 2. Currently, both versions of the TCC prototype only implement a single accelerator core, and per core 1 PE. In the following, we will show the impact of security-related hardware on the execution performance of the accelerator core. For comparison, in the absence of AES-GCM, DSC, and adjust check, we provide the launch plant packets and the get plant packets function for uplift relay on the host, which can directly relay plaintext data packets to TCC in-package memory and thus get baseline performance. Figure 10 shows the latency overhead of the TCC security mechanisms. Even if temporary deployment waits are required, the maximum overhead of TCC doesn't exceed 1.76%. Figure 11 shows the throughput overhead of the TCC security mechanism. Among them, the average overhead of fat core is about 3.5 times that of Xilinx core. This is because the number of multipliers and on-chip buffers of fat core are 4 times that of the Xilinx core. In addition, it can be clearly seen that batch size equals 16 is a turning point in the trend. That is, when the size of encrypted input data package exceeds 16 images, the overhead that TCC can introduce is already minimized smoothly. Security analysis. First, due to our separate memory management between inside and outside the TCC chip, only the outside ciphertext area is visible to the privileged adversary, such as untrusted host OS and other third-party software, while the TCC in-package running memory, the adversary cannot access it. Secondly, TCC doesn't support host CPU to direct access device registers and on-chip buffers and in-package memory through the MMIO path, and the exceptions in the internal calculation process of TCC will not interrupt the untrusted OS. Instead, TCC will package the exception information into response packets and encrypt it and then send it back to the CPU enclave or remote user. Finally, all communications between the TCC enclave, CPU enclave, and remote user are encrypted, and the symmetric secret key negotiated by the three parties is shared by only the three of them. And in addition, the time interval and the size of the sending, receiving, and relaying of ciphertext packets are all data uplifts. Therefore, our TCC system can protect against the adversary's attack. Conclusions. We present the first Secure Accelerator Enclave architecture called TACC, which includes emerging accelerator running AI workloads into the protection scope of T. TACC supports dynamic user switching and context clearing of accelerator enclave from the microarchitecture level. TCC isolates the accelerator and in-package memory from the untrusted host OS to protect against the privileged software attacks. Our prototype evaluation shows small performance overhead of the TCC hardware security mechanism. Thank you for listening.